Thank you again, Pablo, for your nice acceptance to present us a technical presentation about the usefulness of time-resolved Raman spectro-electrochemistry in qualitative and quantitative analysis. Thank you again. I know that for you it was a long day with another two participation of our roundtables regarding the projects that we have in common. And please, if it's possible, if you may introduce yourself and your company a little bit before your presentation. Thank you very much. Thank you again.
Okay, thank you, Michaela. In fact, yeah, I would like to thank you for the invitation to take part in this PRIOCHEM conference. It is a great pleasure, and as you know, it will be even better if I would have been able to be there and to meet you and all your colleagues face to face. But finally, due to some travels with the flights, I didn't manage. In any case, thank you for the invitation. About myself and the company, well, my name is Pablo Van Hul. I have bachelor degree in chemistry, master degree in analytical chemistry, and the PhD in electrochemistry, and mainly with electrochemical biosensors. I did the PhD as well in the University of Oviedo. It's located in the northwest of Spain, more or less on top of Portugal. And when I was finishing the PhD with another colleague from the laboratory called David, and also with the supervisor of our PhD, Professor Agustín Costa, we founded the company called DropSens, and it was in 2006, mainly for the design and the manufacturing of screen printed electrodes that could be used as transducers for the development of electrochemical biosensors. This was already in 2006 that we started just with a couple of persons, David and myself, and just one product, a screen printed carbon electrode. But right now, almost 16 years later, in 2022, we are currently 53 people in the company here, still located in Spain, in Oviedo. And right now we are not called just DropSens, we are called Metrohm DropSens, because 5 years ago we were acquired by a Swiss company with headquarters in Herisau that it's called Metrohm. So right now we are still a Spanish company, but inside a big Swiss group. And now in the whole company, we are not just dealing with electrochemistry, but with some other colleagues from different groups. We also deal with other topics like spectroscopy, ion chromatography, and also with titration. So that's more or less the introduction about myself and the company. And now I will move to show you some of the last results, some of our last R&D activities carried out in the company and related to Raman spectro-electrochemistry. And I will show you some applications for qualitative and also for quantitative analysis. Okay, so about spectro-electrochemistry itself, spectro-electrochemistry is a hybrid analytical technique that combines usually an electrochemical reaction with an spectroscopic monitoring system. This spectroscopic monitoring system could be UVBs, NIR, or Raman. So depending on the optical technique, we can talk about Raman spectro-electrochemistry, UVBs spectro-electrochemistry, or NIR spectro-electrochemistry. The main advantage of this technique is that it is an auto-validated analytical technique accordingly to the definition of the UPAC, because you are getting two analytical signals of the same system at the same time. So in theory, you will not need to do an external validation with another technique. So just correlating these two analytical signals, you can get reliable results. In terms of Raman, it is a very selective technique. It is called a fingerprint technique because it provides this kind of a spectra that belong specifically to each chemical molecule. And in fact, it's very useful for identification purposes, and it can be used in combination with electrochemical reactions dealing with inorganic, organic, or even with biological molecules. Some of the usual disadvantages, some of the usual problems that have spectro-electrochemistry in the last years are always related to the setup, to the experimental setup. Usually for working with this technique, you need a hardware for dealing with the electrochemical technique, so a potentiostat or a galvanostat. You need additional hardwares for the optical monitoring system. And in case we talk about Raman, we will need a laser for the excitation of the sample, and then a spectrometer that will be the detector of the Raman scattering light. In between, we always need the spectro-electrochemical cell where the light is going through and where we have the 3 electrodes of the electrochemical cell. And then usually 2 different softwares are needed. One to control the electrochemical hardware, another software to control the optical part, and even usually a third external software is needed for the data treatment and for the analysis of all the results obtained through the different hardwares. So as you can imagine, we are working usually in research labs, but it's not very user-friendly to deal with 3 different softwares and 2 different instruments. Even the synchronization of both signals from the electrochemistry and the optical side is not easy to be handled. So the idea behind all this research was to try to solve these this kind of inconveniences, of drawbacks. So we work from the hardware side in the integration of the laser, the spectrometer, and the potentiostat galvanostat, everything in one box. So that's what we have here. And also to control everything just with one software. So it will make quite easier and more user-friendly the research activities in the field of Raman spectro-electrochemistry. And also it allows to have very well synchronized data. In terms of the Raman spectro-electrochemical cells, we have different options, or we usually work in the lab with different options. We have one cell for dealing with screen-printed electrodes. So here in the ceramic strip, we have the electrochemical cell with the 3 electrodes, with the working, the auxiliary, and the reference electrode. Usually we place here a drop of solution, just 50, 60 microliters. We cover it with this part of the cell. And in this configuration, we have the Raman probe just on top of the screen-printed electrode. And we have the solution in between the Raman probe and the electrode. We have here 2 fiber optics. One is coming from the laser for the excitation of the sample, and the other one is going to the spectrometer that collects the Raman signal and sends it to the detector. And then here we will have the electrical connections between the electrode and the potentiostat. This is the cell for working with screen-printed electrodes. We have another option when we want to work under flow conditions, but also with screen-printed electrodes. And finally, we have also an option for working with conventional electrodes. So the idea is again the same, to have the Raman proof on top and in front of the working electrode. But in this case, we can introduce external reference and auxiliary electrodes. And usually we work with this configuration, for instance, when dealing with organic solvents that are not so compatible in some cases with the screen printing technology. So we have the different options, and in some of the results that I will show you later, the different cells have been used. Okay, that's nice as a brief introduction, but let's go directly to the to some experimental results to better understand what we are talking about. So I guess that most of you know the benchmark redox couple, the ferrocyanide. So I will show you here in the upside of the slide just a cyclic voltammetry of this redox compound. So I will start with the ferrocyanide, iron 3. And in the cyclic voltammetry, we will reduce the iron 3 to iron 2, and later we will oxidize again the iron 2 to iron 3. And here in parallel, simultaneously and in real time, we will see the evolution of the Raman spectra. And in fact, what we see in the Raman spectra is this band related to the cyanide bond link initially to an iron 3 atom. So we will have only this Raman band. But during the reduction to iron 2, this cyanide band will be transformed in two different bands because the cyanide present different Raman spectra depending if it's linked to iron 3 or iron 2. And then in the backward scan, we will come back to the initial state. So we can see it with the video. So here we have the starting Raman spectra. We reduce iron 3 to iron 2, and then two Raman bands start to arise. The other one is completely deleted. And then in the oxidation process, we can see that these two bands are going down, and the first initial one is going up. Okay, so it's an easy example of how to use the Raman signal to follow an electrochemical reaction. Okay, so let's go to show some more complicated electrochemical systems. So imagine that we have in this case this molecule, resasurin. This molecule can be reduced into different processes, into different steps. First of all, to resoruphin, and in a second step to the hydroresoruphin. And in fact, this second process is reversible, so it can be oxidized again. Okay, so what we do is, and mainly for the identification of the intermediate and the identification of the electrochemical reaction product, is to follow this electrochemical reaction simultaneously with the Raman spectra. In this case, if we start with the Raman spectra with the blue color, that it's the one that we have at these initial potentials, we can see that during this reduction, during this electrochemical process, it is moving from the blue to the orange one. So at a specific Raman sheet, for instance here, we can see the evolution of the Raman band, and even we can see it here as well. For the second electrochemical reduction, sorry. Okay. For the second electrochemical reduction, it is more or less the same. So we can watch this process for the reduction from resoruphin to the hydroresoruphin, looking at different bands. And some of them, like this one, is going down during the reduction process from minus 0.6 volt to minus 1.1 volt. So this is going down with evolution. However, for instance, this one is going up during the process. So having the spectra at this specific potential and having the spectra at this specific potential, we can completely identify what is the intermediate reaction product and what's the final reaction product. Another example of the applications of Raman spectro-electrochemistry for qualitative analysis, because so far I'm just talking about the reaction mechanisms and qualitative assays. So for instance, for the characterization of nanomaterials, for us it's quite usual to modify some of our carbon electrodes with different nanomaterials. It could be single wall carbon nanotubes, multi-wall carbon nanotubes, graphene oxide, reduced graphene oxide. And it's always useful to have information about the state of this nanomaterial on top of our electrodes, the oxidation state, the reduction state. So imagine that you have one of these electrodes completely covered with single wall carbon nanotubes. So we have the D and the G band of the carbon nanotubes. This first one is related to the defects of the carbon nanotubes, and this one is related to the sp2 configuration of the carbon material. And I will show you the evolution of this Raman spectra during a cyclic voltammetry going from 0 volts to +1 volt. Okay. So this is done just in an electrolyte solution in potassium chloride. So I will show you it again. You will see that during this cyclic voltammetry, the band or the ratio between the intensities of the D and the G band is going up because the defects are increasing a little bit, and the sp2 structure is going down. So you can see this band is going down a lot. So the ratio is changing, but in the backward scan, we are coming back almost to the initial state. So we are generating some defects during the oxidation process, but we are recovering the initial structure in the backward scan. However, what happens if we change the electrochemical window and we oxidize up to 1.8 volts? So in this case, we start to generate some defects. We are oxidizing the electrode, but now at very high potentials, we are generating some defects that cannot be recovered later in the backward scan. So here, now the ratio between the intensity of the D band and the G band is much higher here. So we have generated a lot of defects in the structure that are not recovered. So that's not anymore a reversible process. So we are able to understand where are our electrochemical limits, our potential limits to have a structure that can be recovered or completely lost. That's more or less what I saw here in this slide. So initially going from 0 to +1 volt, we have a reversible P doping. However, when we move to up to 1.8 volts, the doping is irreversible. So we are generating too much defects in the structure, and we are not able to recover the initial configuration of the material. In fact, if we follow this ratio, that is usually the one that it's measured, the ratio between the intensities of the D and the G band, it is going up very quickly with increasing in the potential, and it cannot be recovered during the backward scan. Okay. So now that we have entered into the field of materials, and I have shown you some essays with nanotubes, I would like to remark also some essays with organic conductive polymers. This can be used for PDOT, for polyaniline, but I will show you here, for instance, one essay with polypyrrole. In this case, you know that these organic conductive polymers could be generated in situ on top of the surface of our electrodes just by an electrochemical process. So imagine that we start with the pyrrole, with a monomer, with this electrochemical scan going from 0 volts to +0.8 volts. We would like to oxidize the monomer and to generate the polymer, the polypyrrole. So at the starting potential at 0 volts, we have this Raman spectra, but once we are going to higher potentials, we can start to see these specific Raman bands at a specific Raman shifts that allow us to understand that the polypyrrole is being generated. And as well as we can follow the generation of the polypyrrole, also we can understand that at very specific potentials higher to +0.6, 0.7, 0.8 volts, we start to generate a degradation of the polypyrrole. In fact, what happens to these bands corresponding to the polypyrrole is that their intensity is going down at higher potentials. So we can see that the maximum signal is obtained at +0.6 volts, but at +0.8 volts, the intensity of the signal is going down. It is going down because we are over-oxidizing the polypyrrole and we are losing some of the structure. So it provides us a lot of information, and that it's not provided just in the cyclic voltammetry. Because in fact, if you look at the cyclic voltammetry from 0 to plus 0.6 volts, it seems that nothing is happening. So we don't have any electrochemical process. However, we can follow with the Raman spectra that the polypyrrole is being generated. And in fact, if we carry out several voltammograms between 0 and plus 0.6 volts, we can increase the thickness of the polypyrrole that is generated. However, if we go to higher potentials, we are over-oxidizing the polypyrrole and we are losing the structure. Okay, so I have shown you different qualitative assays working with Raman spectro-electrochemistry. These are quite useful for a lot of purposes, but for instance, for quantitative analysis, and if we would like to detect low concentrations of a specific analyte, initially Raman is not the best technique. Usually Raman, it is considered a technique for detection of major components. So it's useful for identification purposes, for the study of reaction mechanisms, but if it lacks of sensitivity. So if we would like to increase the sensitivity, we need to work with this SERS effect, surface enhanced Raman spectroscopy effect. And in this case, due to the interaction of the molecules with some specific metallic surfaces, usually gold, copper, or silver, we can enhance a lot the Raman spectra. So we are able to get information about our sample, but we always need, for going to low detection limits, to have this interaction between the analyte molecule with a metallic surface. And as we talk of metallic surfaces, and we are mentioning gold, copper, and silver, then it's when the integration between electrochemistry and SERS is clearly identified, because we can have metallic electrodes, like a gold electrode or a silver electrode, being used as a SERS substrate for SERS Raman spectro-electrochemistry. So how is the integration of this electrochemistry with the SERS effect? Well, usually working with a metallic electrode, we have two approaches to promote this SERS effect. So the easiest one is just to polarize the surface of our electrode. So we can apply a positive or a negative potential, and we can force some electrostatic interaction with analytes that are negatively or positively charged in our solution. So it can increase, we can module, and we can increase the adsorption or the interaction of a specific molecule with the surface of the electrode. And usually the second approach to generate this SERS substrate in our electrodes, metallic electrodes, is to do some electrochemical pretreatment. So to get some increased roughness in the surface of the electrode, or even to get some nanostructures that will interact with the analyte into the solution and will provide this SERS effect. Okay, so I will show you here a couple of electrochemical pretreatments that we usually carry out with gold and also with silver electrodes to get these SERS substrates for our standard applications. So if we work, for instance, with a gold screen printed electrode that initially has this surface structure, usually we oxidize it in an acid media, for instance, in sulfuric acid. We can go to positive potentials to plus 1.1 volt to get the oxidation of the gold, and also we can produce some dissolution of this gold. And then in the backward scan, we can reduce the gold oxide that we have previously generated. And what we can see in the different pictures of the scanning electron microscope is that we can generate some increased roughness in the surface of the gold particles that we have in the electrode. So we increase the the surface area by increasing the roughness with these nanostructures or with these different shapes that we have in our gold microparticles, and that will be on the surface that it's shares active. However, in this case, if the surface is not pretreated, we will not have the Serres effect. And the same, we can get it with a silver electrode. So in the case of a silver electrode, imagine that just a very low potential at plus 0.3 volts, we can oxidize some of the silver surface. So this is the standard initial silver surface. When we oxidize the silver surface in presence of potassium chloride, we can generate some silver chloride deposited on the surface of the electrode. And when we reduce this silver chloride, so the silver plus is going to metallic silver, we can get these silver particles in the order of tens or hundreds of nanometers in the surface of our electrode. And then these metallic particles that we generate in situ are the Serres active material for our quantitative assays. So now I will show you again with a video that it's easier to understand what I'm talking about. So this is for the detection of a specific molecule, ruthenium bipyridine. And this ruthenium bipyridine, it's adsorbed in the surface of metallic silver once the electrochemical pretreatment of the electrode is done. So here I will show you the electrochemical pretreatment of the silver electrode, and here I will show you the Raman spectra of the ruthenium bipyridine. Initially, at this potential, we will not have any Raman spectra because there is no interaction between the molecule and the silver. But after the pretreatment of the electrode, we will see how the Raman spectra is arising. Okay, so here we start to reduce the silver, we generate the particles, and then we can see the Raman spectra. And even in the backward scan, when we oxidize again the silver particles, we almost lose all the Raman spectra. It's not completely lost, but you can see clearly how the Serres effect is obtained mainly at these negative potentials, and then how it is going down. Okay, so following this methodology and having different concentrations of ruthenium bipyridine in solution, we were able to detect this molecule with limits of detections below 50 ppts, parts per trillion. So it means that this Raman with a Serres effect is really sensitive. Okay, we have obtained different limits of detection for different molecules, and we can have some of them in the order of ppts, some of them in the order of ppbs, and some others in the order of ppms. It depends always on the interaction of the molecule. It depends on the chemical structure and also in the interaction of the molecule with the metallic surface, with the gold, with the silver, or even with copper. I will show you another example, but in this case with the gold material, because the previous one with the ruthenium bipyridine was made with silver. So in this case, it's for detection of some pesticides, thiram, imidacloprid, chlorpyrifos. Initially, we have this gold surface and we don't have any Raman spectra, but after the oxidation of the gold and after the reduction of the gold, and once we have this surface in our metallic electrode, is when we can get the Raman spectra of the different molecules. Even in this case, we added a first a small pre-concentration step. So just reducing the volume of the drop of solution on top of our electrode. And with this process, we were able to get detection limits between the legal limits referenced by the European Union. So for the thiram, we are in 2.4 ppbs, imidacloprid 25 ppbs, and chlorpyrifos 3.5 ppm. Okay, so we have seen at the beginning some examples of qualitative assays, some examples of quantitative assays with different surfaces. And now I would like to show you to combine a little bit what I have mentioned before. And imagine that we, in this case, we are using Search effect. We are using Search effect in a gold electrode. So we oxidize the gold and we reduce the gold to generate the specific surface that we need. But in this case, it is made just to follow, or for a qualitative purpose, just to follow this electrochemical reaction. So here we have this reversible process that corresponds to the reduction of the quinonimine to paraminophenol and to the oxidation of aminophenol to iminoquinone. So we carry out the electrochemical process here. We will see how we oxidize the gold electrode, how we reduce it. And once we have this, we have done this electrochemical process and we have the Search active substrate, is when we will get the spectra of the aminophenol, and we can see the change in the spectra, and we can get as well the spectra of the iminoquinone when it has been reduced. So here we are just working in the gold surface. Here we are working in the gold surface, getting this Search active. And now that we have it, we have the spectra of the aminophenol. Now that has been reduced, we have the spectra of the iminoquinone, and one that has been again oxidized, we got the spectra again of the aminophenol. I will show it again. There is no change in the Raman spectra. Now that it's Search active, we have the spectra of this molecule. Now we lose it because we have this other one that has been reduced, and now that we oxidize again, we come back to the paraminophenol. So in this example, we are combining a Search active substrate that it's obtained with the oxidation of the gold, but just to get qualitative assays. So to follow this reaction and to understand what could be the reaction, or what will be the product of this electrochemical reaction. We have done the same, for instance, in an organic media, and in this case with ferrocene and ferrocenium. So in this case, we have here the electrochemical process of ferrocene, how is it oxidized to ferrocenium, and how is it reduced to ferrocene. And we can follow again the change in the Raman spectra due to this electrochemical process. But here again, we need to have previously a Search active substrate to being able to follow the reaction. So some final remarks, some conclusions. I think, or we think, that the Raman spectro-electrochemistry is very powerful for the study of different electrochemical and chemical systems and processes. It provides us a lot of information about materials, species. It's very useful for the identification of reaction products. It's very relevant to work with this technique always in situ and in real time. Some people is working with Raman spectro-electrochemistry ex situ. So you do some electrochemistry in your cell, and then you took the electrode and you move it to a Raman microscope, for instance, but you are losing a lot of information. You are not working with time resolution. And you have seen, for instance, with the nanotubes, with the polypyrrole, with all these other molecules, that it's really changing a lot just in 100 millivolts and just in 1 second. So you need to follow it in real time and in situ. We had to develop different cells depending on the electrodes we were willing to use. And finally, as you have seen with all the quantitative assays that I have shown, that the electrochemically assisted search is very useful to avoid any lack of sensitivity of the Raman spectroscopy by itself. And finally, as I have shown you, it is not only a technique that it's limited to work with aqueous solutions, but we can work also with organic media. And that's all from my side. So thank you for your attention. And if you would like to make any question, comment, that's welcome.
Much, Pablo, do you hear me? Yes.
Yes.
Okay, thank you very much. It was a very nice presentation, very clear with these movies, you know, to present this very didactic, very and easy to understand. If there are some questions from the conference hall or from online, because I have some questions, but if Ana Maria?
Ana Maria, yes, I have one question. Can we use some techniques, such techniques for our purpose, for example, for nitrate monitoring?
Well, that's a good question. I think we have not tested to follow the oxidation, for instance, of nitrate to nitrate, but I guess it could be feasible. In fact, working just with Raman and not with Serre's effect, we just will need to work with a high concentration of nitrate, and we should get the Raman spectra of the nitrate, and we can get how is it oxidized to nitrate. Yeah, initially it could be tested. In this case, at least the electrochemical process is quite well known, so we know that nitrate is oxidized to nitrate, and usually it could be more useful when you don't know what could be your product. So you carry out an electrochemical reaction, and with the Raman spectra that you get at the end is when you go to a library, for instance, and you can understand, okay, this is the product of the enzymatic of the electrochemical reaction. Sorry.
I mean, also for the samples in food and not only from agriculture. So it is useful. Thank you, Pablo.
Yep.
Much, Ana Maria. My questions, I have two questions. One is regarding the selectivity of the method, because if we have 2 or 3 compounds there, I don't know if we can perform
Yes.
At least quantitative. I don't know if we can do. What do you think?
Yeah, it's a very interesting question. In fact, since the Raman spectra are so selective for each molecule, the peaks are very sharp and very narrow. So even we can get a Raman spectra of a mixture of 4 or 5 different compounds, and we can easily identify them. We have done it with different vitamins B. So we were working with a pill, with a pharmaceutical formula with 5 different B vitamins, and we were able to identify all of them and even to do the quantitative analysis. So we were able to oxidize some of the vitamins, and we were able to see how some of the bands at a specific Raman shifts are going down and some others are going up. And usually, if you just have one band at a specific Raman shift that it's specific of one of the molecules that you have in your matrix, you are able to do the quantitative analysis just with the evolution of such band. So it can be done. It is not as easy as if you will have just one, but Raman is very selective. So it's very useful for this.
And for so besides the pre-concentration of the sample, we need also a little bit to a purification step, no? Anyway, if it is a complex matrix.
Well, Raman by itself, when we think about Raman analysis with these portable systems or even benchtop instruments, they are applied directly to real samples, and even they are applied directly through the container of real samples. So imagine that you are getting a bottle or a plastic bag with some sample inside, and you even don't need to open it. So the Raman can go through the container, and you can get the Raman spectra of the real sample. If you use it in this way, you will be able only to identify the major components of the sample, because Raman is not very sensitive. So you will be able to identify the major components. If you like to go to low detection limits, you always need to get this surge effect, and you always need to do some sample prep, sample dissolution or sample extraction or whatever.
Okay, thank you. So this was the first question, and the second, beside the gold and the silver, what other materials for electrodes do you think that may be used?
Here we have always to differentiate between the qualitative assays and the quantitative. Okay, for the qualitative assays, everything I have shown is just based on carbon electrodes. So we can follow electrochemical reactions, ferrocene, ferrucinium, ferrocyanide, ferricyanide, polypyrrole, PDOT, nanotubes. All these qualitative assays were carried out on carbon electrodes, so we don't need any special. If we would like to go to quantitative analysis and mainly to low detection limits, is when we need this surge effect. And when we need this surge effect, the interaction of the molecule should be done with a metallic electrode. And here, about metallic electrodes, we have gold, silver, copper. There are also some papers based on platinum, but it's not so clear what is the interaction based on. But usually the best metals with a surge effect are these three: gold, silver, and copper.
And the graphene, do you think that, or it was tested, or there are some chances to try with graphene?
Everything that we have done with graphene was not to get any surge active material, that we have not tested it, but we have done a lot of assays, as I have shown with the carbon nanotubes, just to follow for instance, the reduction or the oxidation of graphene. So imagine that you have an electrode based on graphene, you have just an electrolyte solution, an acid media or potassium chloride, and with your Raman probe, you are just looking at the surface of your electrode. So you are able to see how the graphene is being oxidized, how the graphene is being reduced, and you can follow it just with the Raman bands of the graphene that are changing. But that's our only experience with Raman and graphene.
Anyway, it's very interesting also for characterization of materials and to see the defects and or to control if you need more or if you need less to control them.
It's in fact for such application for us it was very useful, because when you are looking just to the electrochemistry, you don't get any information. I mean, you can carry out an oxidation and reduction of graphene or carbon nanotubes or whatever in an electrolyte solution, and you don't have clear anodic or cathodic peaks due to the material by itself. So with electrochemistry, you are not getting information, but from the Raman spectra, you are seeing, or you are able to watch that a lot of changes are being produced in the material, because the Raman is very selective and very useful to watch these changes that cannot be followed with electrochemistry. And it's the same with the organic polymers. With the polypyrrole, at the beginning, we think we were not oxidizing the pyrrole to get the polymer, but even just going up to plus 0.6 volts, the polypyrrole was already generated. But it needs to be watched with the Raman, or to be monitored with the Raman.
Yes, thank you very much. It is very interesting, and we will think to exploit this combination of techniques.
Okay, thanks to you.
Thank you,
welcome.
and see you, I hope, very soon in Bucharest. And
yeah.
we wait you to collaborate, to continue our collaboration. Thank you very much, Pablo.
Yeah, thanks to you, and thank you for the invitation to participate in PRIOCHEM, and we will see for sure in the near future there.
Thank you. Bye bye.
Thank you. Bye bye.